Hello there. We will look at rational expressions now. We'll look at the basic properties of rational expression and how do we reduce rational expression to the lowest terms. Um, so the two basic properties associated with rational expression go on to apply one of the properties, how to reduce to the lowest terms, as we said, right? So what is a rational, if you recall in one of the previous videos, rational expression, okay? They are a let's look at rational numbers first. Rational numbers. And we said that a rational number is something that's written as A over B, some sort of a ratio, where A and B are integers, but B cannot be equal to 0, okay? So we've talked about ratio in the past, rational numbers, and we said that the denominator of any fraction cannot be equal to 0. Now, a rational expression is defined similarly, okay? So when we speak of a rational expression now, defined similarly, and we say that a rational expression is when we have some sort of a fraction also, and we say that's P over Q, generally P over Q, where P and Q, okay, where P and Q are polynomials, okay? Polynomials, and P and Q cannot be equal to 0, okay? So that's the difference between the rational number, okay? Rational number, we're looking at integers, but a rational expression, now we're speaking of a polynomial. So some examples, right? If you're looking at examples, well, we have, for example, 5x minus 1, that's a polynomial. And if we divide that by some other polynomial, 2x plus 3, okay? So this is one example of a rational expression. Another example we can look at is a quadratic, x squared plus 2x plus 1 divided by x squared minus 4. Okay? Another example can be x over x plus 1. These are all examples of a rational expression. Okay. Now, some basic properties that will help us. Okay, we will look at some of the basic properties. And that is that if we have a rational expression, okay, when we multiply or divide the numerator and denominator, okay, by the same non-zero expression, may change the form of the rational expression but it will always produce an expression will always produce an expression equivalent, and that's very important, equivalent to the original. So let's start off with something we know, okay? If we have, and this goes back for also when we had rational numbers, okay? Let's look at the rational number 1/2. And we know that if we multiply the top by 3 and the bottom by 3, this is equivalent to 3/6. Okay? Now, although they may look different, these two things are exactly the same. Okay? These two things are exactly the same. We can also think of, how about if we had 12/36? 12/24. Okay? You will see that if you now divide by a number and keep dividing, okay, if you divide top and bottom by 12, you will get 1/2. Okay, so by multiplying, and these two things here are exactly the same. Okay, now for rational expression, if we have a rational expression P/Q, and we multiply the top by some polynomial k, or divide it by k, this is equivalent to P times k over Q times k. Okay? And the same will happen if we divide. Okay, if we divide it by Q and by k. So by multiplying or dividing, it doesn't change. Okay. Now with this whole idea, we can use this property to reduce rational expressions. So let's use the property to reduce rational expression. Okay. So example, reduce x squared minus 4 over x minus 2, okay, to its lowest terms. Now, one of the things we must do whenever we're reducing is always try to simplify or factor numerator and denominator. So you will see we can factor the numerator, okay? Because it is difference of squares, okay? So we have x squared minus 4 over x minus 2 is the same. By factoring, we get x squared minus 2 squared over x minus 2, which can also continue to be x minus 2 times x plus 2 over x minus 2, okay? So maybe here we should say rewrite, and here is where we factor, okay? So this is now equivalent to x minus 2 times x plus 2 divided by x minus 2. And now you will notice that this numerator will cancel with that denominator, leaving you with x plus 2. Okay. So this is our simplification. Well, you can say x plus 2 over 1, which is equal to x plus 2. Okay. So there is a simplify by factoring. Okay. Now notice here that in your example, you would have seen that if x is 2, okay, that there would have been a problem. Okay, if x is equal to 2, you will get 0 over 0. Okay? And we know that 0 can never be in the denominator. So later on, we'll talk about numbers that make the denominator equal 0, the restrictions we call them. Okay, so here's another example. Reduce. Sometimes we say simplify. Yeah. How about if we have, so example, we have a squared minus 5a minus 6 over a squared minus 1. So let's try to factor the numerator, and also we want to factor the denominator. Okay. So if we factor the numerator, okay, using the master product method or using the guessing method, this becomes a minus 6 times a plus 1. Okay, divide that by, in the denominator it's difference of squares, so it's a minus 1 times a plus 1. And now we look for anything that are alike in both the numerator and the denominator. And we see here that this is the same as this, so we can cancel it out, which really becomes 1. So this is equal to a minus 6 over a minus 1. Okay. So there are many different ways, okay, which this can be done. The key point is that factoring is a very important part of reducing. Okay, very important. Let's look at another example. Reduce. If we have 2a cubed minus 16 divided by 4a squared minus 12a plus 8. Well, let's try to factor again. Let's look and see if we can factor the numerator. And let's look and see if we can factor the denominator. Well, I notice both in the numerator and the denominator, they're GCF. The GCF in the numerator is 2, so if I take out 2, I have a cubed minus 8. And in the denominator, 4 is common, so we have a squared minus 3a plus 2. Okay, and please make sure when you draw this line that it's covering everything in the denominator. Okay, now we can also factor once again. The inside here can still be factored, and same thing, you can try to factor the inside here. Okay, now the top is difference of cubes. Okay, and I had shared the difference of cube formula with you before. So if you factor the inside, the 2 stays, but now that inside, using the difference of cube, becomes a minus 2, okay, times a squared plus 2a plus 4. And if you factor the denominator, the 4 will stay. And then if you factor this quadratic here, okay, factoring that quadratic will give me a minus 2 times a minus 1. Okay, so you may want to recall or refresh difference of cube formula. Okay, let me rewrite that for you. So the numerator is the difference of cube. Okay, so if you look that up in your notes, the difference of cube. Now if you look here, this is exactly the same as that. And also 2 and 4 can be simplified. So if you divide the top by 2 and the bottom by 2, can't really write it that way. Okay, this can be simplified. 2 over 4 is the same as 1 over 2. And we have left, which is a squared plus 2a plus 4 over a minus 1. Okay, there is no need to write the 1 here, so I can rewrite this as a squared plus 2a plus 4 over a minus 1. Now notice, okay, please note that this is quadratic. So why didn't I try to see if I can factor that? Well, that goes back to the difference of cube formula, okay? The difference of cube formula. And if you look back at notes, the difference of cube which states that a cube minus b cube, by factoring, this is a minus b times a squared plus ab plus b squared. And notice that this here is a quadratic, and that quadratic is a prime polynomial, which means that they wouldn't be able to factor it. Okay, cannot be factored. It's a prime polynomial. So you may want to look back at the difference of cube and the sum of cube, okay? And that's how I am getting this information here, okay? That's where I'm getting it from. Now let's look at another example. Simple reduce. How about if I ask you to reduce A minus B over B minus A? Now, notice that A minus B is completely different from B minus A, okay? But you will see that if we factor -1 from each term in the numerator, okay, if we factor -1, factor -1 from the numerator, this becomes -1, but then in parentheses, okay, we will have minus A plus B. And the denominator will still be B minus A. Okay. Now you will notice that in this parentheses here now, that's the same as if I write -1 times B, times B minus A, because the sign of the B is positive and the sign of the A is negative, divided by B minus A. And now this numerator is exactly the same as that denominator, so the final result is equal to -1. Okay. Now you could have, if you wanted, you could have factored -1 from the denominator and rewrite the denominator. That would have also been correct. So you didn't have to factor -1 from the numerator. If you wanted, you could have factored -1 from the denominator, and then you would have gotten A minus B also, and then the top will still cancel with the bottom. Okay. Let's look at another example. Factor reduce. Reduce. How about if we have x squared minus 25 divided by 5 minus x? Well, we can start off by factoring numerator. And we can also see, can we factor the denominator? Well, clearly we can see that the numerator is difference of squares, so x squared minus 5 squared, and there is nothing common, so that's just 5 minus x. So right now we cannot factor the denominator. There's no GCF. And now we can factor. So if we factor this using the difference of squares, we have x minus 5 times x plus 5 divided by 5 minus x. But this here is not the same as this. They're different, okay? These are different. These two things are different. So what we can do, let us factor -1 from the denominator. Okay? And if we do that, the numerator stays the same, x minus 5 times x plus 5. But if we factor -1 from the denominator, this will leave me with minus 5 plus x. And here I can rewrite the denominator so the numerator stays the same, divided by -1 now, times the denominator, writing the x first, it's positive, and then a minus 5. And now you will see that this is the same as this. And because they're the same, we can reduce them or cancel them, as we say. So that leaves me with x plus 5 divided by -1. Okay? And we said that we generally don't leave a negative in the denominator. So if I put it in the numerator, it becomes x plus 5 over 1. And we don't have to write it over 1. So finally, we have negative x in parentheses plus 5. And that's our final result. So since we're looking at rational expression and how to reducing them, there is also something, okay? We also have what is called rational functions. Now, we haven't really talked about functions yet, okay? But since I'm looking at rational expression, I might as well throw out there what a rational function is. So functions are generally written as f of x, g of x, meaning function of x, okay? F of x means f is a function of x, and that is equal to, okay, p of x over q of x, where p of x and q of x are polynomials, okay? And note, q of x cannot be equal to 0, okay? So functions is just some sort of a machine or a mathematical expression where you're able to put in some sort of a number or letter and you get something out of it. For example, let's say, okay, let's look at the function, the rational function f of x equal to x minus 1 over x plus 2. And if I ask you to evaluate or to find f of 0. So what this means to replace x with 0. So f of 0 is equal to, well, let's use the same color, f of 0, notice that I'm plugging in 0 now for x, and that is equal to 0 minus 1 over 0, oops, made color, 0 plus 2. So wherever I see x, I replace it with 0, okay? And evaluating this, f of 0 is equal to minus 1 over 2, okay? So evaluating is just we're plugging in some sort of a number in place of that letter, okay? That's all we're doing. Now, and you have probably done a lot of these before. But I don't want to go in too much detail enough about functions now. What I do want to bring to your attention is the domain of rational functions, something called the domain. And the domain of a function is all acceptable values of that function. Okay, so we'll talk about later again something called the domain of a function. And the domain of a function, when we talk about the domain is the set of all acceptable values of the function. Okay, the set of all acceptable values. So for example, if I give you the function f of x, and let's use the same function we had before, x minus 1 over x plus 2. And remember, right, recall that denominators, okay, denominators cannot be 0. So that means that x plus 2 cannot be equal to 0. And what x value will make this happen? Well, if we minus 2 on both sides, we will see that x cannot be equal to negative 2. And clearly, right, clearly you will see this is true. So if we look at the number line, and we take out negative 2, what's left on that line? Well, on this side here, we will have from negative infinity to negative 2, parentheses, negative 2 is not included. And on this side here, we will have from negative 2 to positive infinity. And by unioning it, that brings it together, which we've also seen when we did solve inequality. So the domain of this function is minus infinity to negative 2, union with from negative 2 to 8. Now, although you're seeing negative 2 here, remember there's a parentheses, so negative 2 is not really part of it, okay? Very, very close to negative 2, but not exactly negative 2. So keep in mind what the domain is, okay? What is the domain? Now, how about if we look at another example? Suppose I tell you that, example, find the domain of g of x equals 2 over x minus 1. So you probably can look at this and say, well, here, if x is 1, there's a problem. So x cannot be 1, right? Well, I want you to get into the habit of at least trying what I'm doing right now, because sometimes you wouldn't really be able to see it. So we know that x minus 1 cannot be equal to 0. And by solving this for x, we see that x, this becomes 0, cannot be equal to 1. And if you draw the number line and you take out 1, if you draw your number line and you take out 1, what do you have left? Okay, what is left in this line? If this is 0 and you take out 1, well, on this side here, you have from negative infinity going all the way up to 1. Okay, and then on this side here, you have from 1 to infinity. From 1 to infinity. Okay, and bringing the two of them together. So the domain of this function would be from minus infinity to 1, union with from 1 to infinity. Now there's much more. What happens if the denominator is not a polynomial? What happens if I have a function and the denominator is not a polynomial? And in my video with functions, okay, we talked about different scenarios. So function is a totally different video. I have explaining functions, but I just want, since we're looking at rational expression, is to throw in there to give you a head start about functions. Okay.